So we're going to do two today. We'll do transformations and we'll do post hocs because we can. They're the two short things. This will take 10. This might only take 10 minutes. The other one might only take 10 minutes. But feel free to ask questions. Feel free to ask questions. We're right where I think we should be in the class, so there's no concern there. Okay, so let's say you've done your exploratory data analysis, right? You've looked at your numbers. You see what looks like a difference. That's what you're always after. It looks good. The graph looks good. You do an analysis of variance, and you literally get nothing. You get a non-significant effect. Now, there's a couple possibilities. It could be literally nothing happened, but if you've done the EDA and you look at it and do some graphs, you go, there's a difference here. But my statistics aren't telling me what I know. And the purpose of inferential statistics is for them to tell you what you already know, to confirm what you found. Okay? That's their job. Maybe you violated an assumption. Now, if you violated the independence of events assumption, you're screwed. You're not very good at experimental design. So that's your problem. However, there are times we violate assumptions that are less fixable. Usually it's the homogeneity of variance assumption we violate. So really, variances are way different. And what is way different? One's 4 times the other. That's sort of and that's just a rule of thumb. Okay. ANOVA is pretty robust when it comes to violations of that assumption of homogeneity variance, but it can. And the nice thing is, the more you violate it, the more conservative the test becomes. So you're actually less likely to make a fool of yourself, which is nice. It's not like you violate an assumption. You go, there are psychics. So you don't come out saying something stupid. But if there actually are psychics and you miss it, that's a shame because Nobel Prize. There aren't any psychics. Okay. You like that transition? That was pretty good, eh? So what can be done? Or as Lenin once said, what is to be done? Yes, I just quoted Lenin. Not John, Vladimir Ilyich. Well, we can transform our data. What we're going to do is we're going to take the numbers and do some mathematical thing to them. Okay? Some sort of mathematical operation. It may be as simple as adding 5 to all of them. That would seem strange. But that would be, And so you hear people say, well, it's not fair. You can't just do that to your numbers. It's like, you can't just... Sure, why not? Think about what I had you do in the very first assignment. I had you turn centimeters into inches. That's not alchemy. That's not lead into gold. They both measure length. Oh, okay, that's fine. What if I had you take all the values, multiply them times 9/5, and added 32? That sounds weird. Except all I just did was convert Celsius into Fahrenheit. Or peace-loving, free-thinking degrees into, bourgeois running lackeys of the capitalist degrees. Again, kind of going with the Lenin thing today. That actually sounded more North Korean than anything. So it's actually perfectly fair. There's nothing wrong with doing this as long as the units make sense. Celsius and Fahrenheit both make sense. There's nothing inherently better about Celsius. There really isn't. I know we were all drilled into our heads because we live next to the States and they use Fahrenheit. It's better because 0 and 100. That doesn't make it any better. It's just different, and we use the same thing that everywhere else except the United States, Liberia, and Myanmar use. And Myanmar. So, there's nothing wrong with it. So it is so fair. You're just changing the units. It's like changing Canadian dollars to American dollars. It's still money. Right? I've always thought the ultimate, we shouldn't allow anybody to get a degree without them actually being able to calculate it. Is it cheaper to get gas in submission? And you have to factor in crossing the border and putting in, first of all, to pay your money to go across the bridge and come back. Plus, you have to do the conversion, and you have to convert to Canadian dollars and convert US gallons into liters. If you can do that, you're fine. If not, you should have to take a remedial math class. A number of times, I'm going across. Everything's cheaper there. You realize we're a dollar and Sorry. Kind of bugs me. Not in a nationalistic way, in a math way. Okay. Who knows what a logarithm is? You guys know what logarithms are? Put your hand up if you know what they are. If you don't, I will teach them to you very shortly. Oh, you know what they are. I'm so happy. Someone knows. Teach it to us. No, I'm kidding. It's actually not that hard. Okay. You take a logarithm of a number on this chart. Okay. So logarithm base 10 of 100 is 2. Logarithm base 10. If you don't write 10, it still means 10. It's still 10. That's sort of the standard. 10 is 1. Logarithm of 3. You see the pattern? Right? If you didn't learn this in high school, which you did, you just forgot. It's the exponent, and that's the base. 10 squared is 100. 10 to the first is 1. 10 cubed is 1,000. What's that? Yeah, logarithm. Yeah. By the way, there was nothing funny when I was in high school. You'd simplify these equations, and the math teacher would say, then you drop your logs, and everybody goes, So, not even sure what it meant. We all laughed. Because we were idiots. What's this? You see what it does? It takes really big numbers and pulls them way down more than small numbers. Like 1,000 becomes 3. 100 becomes 2. 10 becomes 1. 1 is 0. 10 to the 0th power is 1. Oh? That's just a thing. Again, you learned it in high school, you forgot. And you might say, that's weird. That doesn't seem right. Let's see, what's something that's a logarithmic scale? Oh, Richter scale of earthquakes. A 6 is 10 times more powerful than a 5. A 7 is 10 times more powerful than a 6, and 100 times more powerful than a 5. So when you hear there's been an earthquake and it's a 4.5, and it's in California, and people just kept walking around not caring because they're used to the earth shaking a little bit. Or you hear that we had one here about 5-6 years ago, and it was about a 4 point something centered in near Ottawa. It shook a little bit here. And then, a few days later, there's one in like California, and it's like there was one in, what was the Fukushima one? Yeah, it's one in Japan. It's like a 7. You're like, well, it's only 1.5 more. No, that's like 1,000 more. Or 100 more. So, yeah. Okay, so that's a log scale. Decibels are a log scale. 90 decibels is 10 times louder than 80 decibels. So we do that all the time. It's a thing we do in math all the time. In fact, those of you that have taken brain behavior with me have seen the graph that has the effective dose, the ED50 for various antipsychotic drugs, and the dopamine 2 binding efficiency. That's a log graph if you look at it. And that's a straight line when you make it into a logarithm. So you get an exponential curve like a reaction time. Take the log, it becomes a straight line. Reaction times have exponential. Like if you have fatigue, or how tired somebody is, in reaction times, it's exponential. So why not just take the logs? Easy peasy. Negative values are a problem. You can't take a negative of a log. You take the log of a negative. Okay. So what you do is just add a constant first. So let's say you got a number. Let's say the lowest number you have is -10. I don't know. Let's say we add 10 to all of them, and then take the logarithm. That's perfectly acceptable. It's perfectly acceptable. You very often won't use. So yeah, that's like this, log of x plus k. You're often not using the log base 10. You very often use the natural logarithm. So instead of log, it's written as ln, ln. Okay, so you'll see that on your calculator. That's just the equivalent of log to the base e. If you remember, e was actually in the e is a constant. It's one of those weird mathematical constants. It's in the equation for the normal distribution. Remember that. It's roughly 2.71828. A lot of natural phenomena that are exponential, the base of those curves is 2.71828, just a figure. It's like pi, except it's got nothing to do with circles. For pi. Okay. Questions about that? It's not so hard, right? I just showed you on the SPSS how to do a transform. You can make a new variable, just say take the logarithm of all these. It's done. Or you could get out your calculator and do it yourself. Fun. Okay, questions so far? Don't feel bad. I mean, this is really, and I know I keep saying you learned this in high school, you've forgotten it. Don't feel bad. Don't feel like you shouldn't ask a question because you've forgotten high school math. That's okay. Not many of us take logarithms on a daily basis. It's not the kind of thing that comes up. Okay. Square root. Now you know what square roots are. I don't have to explain square roots. I'm not explaining square roots. I'm sorry. I'm just not going to do it. Because I know you all know that one, because we have it in our formulas, a lot of our formulas. Square roots are funny. What they do, and you know this, is they make big numbers. They kind of do what logarithms do. They take big numbers and make them smaller, and small numbers just a little bit smaller, but not nearly as, what's the word for it? Not, intensely isn't quite the right word, but you know what I mean. I hope. Okay. Use of counted data. So how many times did you, how many trials did you get correct? When you do this, when you end up with counted data, you often get a situation where your means are proportional to your variances. So as the means go up, let's say the mean doubles, the variance doubles. So it's proportional. And that's bad. We want the variances to be the same. And a neat thing that square roots do is they actually fix this. You take the square root of the original number. You might want to add a constant first. Again, because you don't want negative values. Right? Because then you get into imaginary numbers and things that doesn't help anybody. Okay? Well, add a constant first. Nothing wrong with that. And this is just typically done. You go, oh, it's counted data. Take the square root. What about the reciprocal? You know, you flip the fraction over, just flip it. So you take the reciprocal of value. When would you do this? This actually makes your range a lot smaller, so the variances get smaller, the range of your scores. This is almost always done with latency, so you're measuring elapsed time. All you're doing in this case is converting time to speed. Speed really is just a reciprocal of time with the constant of distance put in there. Right? Think about it, kilometers per hour or hour. Well, now hour's on the bottom. This is nothing. So again, this isn't something that's hard to do. And mathematically with a computer, it's trivial. You would literally, when you did the transform thing in SPSS, you would just say transform, this is new variable, and you can pick a bunch of mathematical operations, and it just does it. And that's now your new dependent variable. This is a weird one. Now we're getting weird. It's getting a little wacky now. A little wild. Trigonometry. That's right. Oh yeah. I went there. Arcsine. Okay, I'm not even going to try to explain this to you. An arcsine is the inverse of a sine. You know, you take a sine and you get radians? Well, this does the opposite. Again, you probably did this in high school. It doesn't matter that you remember what arcsines are. It matters that this is easy to do and it fixes a problem. When you have proportions, percent correct, the number of times my students, a lot of times my honor students do memory experiments, because that's sort of my thing that I do. It's either memory or weird things with shapes. That's the other thing I'm interested in. I have Very strange interests science-wise. So they get these percent correct scores. This group has 60%, this group has 40%. You look at it and go, that's different, and they get nothing. And I say, oh, did you do an Arcsine transformation? And they go, did I do a what with a who now? And I say, why didn't you pay attention last year when I taught you 3256? It's a proportion. You're probably going to violate an assumption. But what we want to do is we want to stretch out both tails. You're more likely, think about this, with proportions, let's say it's a 50-50 chance, you're more likely to get a lot of scores in the middle and very few scores that are really low or really high. Right? It's easier to get 50 or 60 or 40 than it is to get 100 or 0. It's hard to get 100 on anything out of 100. It's hard to get 0 in anything either out of 100. If you have the alternatives in front of you, is what I'm saying. It's easy to get 30, circled all the B's. Right? You know, there was a study done that time, and I heard about it, and 25%, 50, the University of Washington is 58% of the time the answer is B. We all heard that in first year, right? Except it was B or C or D or A. Actually, 25% of the time it's A, 25% of the time it's B, then there's C and D. Now there's 5 alternatives. Anyway, let's stretch it out. And that's what the Arcsine transform does. Whoa. Actually, it's not just the Arcsine. It's 2 times the Arcsine, and before you've done that, you've taken the square root of the variable. What? It pulls out the tails, it pulls out the middle and makes them the same, distribute the same way as the tails. I would take my word for it if I were you. And again, the number of times when I've had honor students who have done memory experiments who have thought they didn't find anything, and I tell them, you didn't transform your data, and they go back and they go, oh, I forgot, that's right. And they do it, and they find something. But when do you do this? When do you transform data? You don't always transform your data. You don't go, well, I have data now, I may as well mathematically torture it until it tells me what I want it to. That's not what you're supposed to be doing here. You do it when the variances are messy, because it fixes variance problems. It doesn't fix other issues. Transformations fix variance issues. That's all they fix. Okay? And I've given you some rough guidelines. It's basically, any stats book would give you, or website, would give you these same guidelines. If your data does not violate an assumption, you don't transform the data. I had percent correct in my PhD dissertation, and it didn't violate any assumptions. And I remember my supervisor saying, aren't you going to do the 2 times the Arcsine square root? And I said, I don't have to. Because it's harder for the reader to understand what it means. I know what 100% means. I know 100% correct is good. I don't know what the value is for 2 times the Arcsine square root of 100. I just don't know. So it's easier for the reader if it's untransformed, which is why you present untransformed data in a graph. You present untransformed data, you show your error bars are ridiculously different. You go, of course, I transformed this. Right? I did an Arcsine square root transform because, as you know, these are proportions, and that's what people do. That's the thing that people do. So this is really not. This is where I had to put this somewhere, this little mini lecture, so I put it here right after we did analysis of variance. Do you have questions? Okay. So that's one miniature lecture